Let's talk about a word you hear all the time: algorithm. It sounds super technical, right? Maybe a little intimidating, but I'm going to let you in on a little secret. It's something you already use every single day.
So let me ask you this. Have you ever baked a cake from a recipe? Or, put together some of that famously confusing flat pack furniture? Well, if you have, then congratulations, you've already mastered using an algorithm.
I mean, think about it. A recipe is just a simple step-by-step process. It tells you exactly what to do and in what order to get a very specific result. In this case, a delicious cake. It's the perfect real-world example of what an algorithm is all about. And that brings us right to the official definition. At its very heart, an algorithm is just a clear set of instructions for solving a problem. So whether you're baking that cake or a computer is searching the entire internet, the basic idea is exactly the same. Now hold on, not just any to-do list gets to be called an algorithm. To really earn that title, a set of instructions has to play by a few simple but really important rules. So what are these rules? Well, first, finiteness. It has to end. Your cake eventually comes out of the oven. The process doesn't just run forever. Each step has to be definite and super precise. Mix until combined is good. Mix for a little while, not so much. It needs an input, that's our flour and sugar. And it has to produce an output, that's our finished cake. And finally, effectiveness. Every single step has to be basic enough that you can actually do it. Okay, so we know what an algorithm is, but here's the next big question. Are they all created equal? If you have two different recipes for the same exact cake, could one be better? Well, in the world of computer science, the answer is a huge yes. Just imagine you're trying to find someone's name. On one hand, you have a perfectly sorted phone book. On the other, a giant, messy pile of papers. You'll find the name in both, for sure, but the phone book method is going to be way, way faster and more predictable. This shows us that how you design your algorithm, your method, makes all the difference. And this is the crucial point. For computers that are doing billions of things a second, efficiency isn't just a nice-to-have, it's everything. It's all about solving the problem in the fastest, most resource-friendly way possible, which means, of course, we need a way to measure that efficiency. And that's where this kind of scary-sounding thing called Big O notation comes in. But don't let the name freak you out. Just think of it like a performance rating, or maybe a nutrition label for an algorithm. It tells us how the algorithm's speed will change as the problem gets bigger and bigger, specifically in the worst-case scenario. So let's quickly break this down. O1 is the gold standard. It's lightning fast, taking the same amount of time no matter how big the task is. Then you have O of n, which is linear. That means if the job gets twice as big, it takes twice as long. That's our messy pile of papers. And something like O(n squared, well, that gets slow really fast, because the work grows exponentially. Big O is just the tool programmers use to compare different approaches and pick the best one for the job. So if you're a programmer trying to solve a really complex problem, you don't just jump in and start typing code. That'd be like trying to build a house without a blueprint. You need a plan. You've got to have a plan first. And in programming, that plan is called pseudocode. It's just a way of sketching out the logic of your algorithm using plain English. It's like a universal blueprint. Any programmer can look at it and get the logic, no matter what coding language they actually use. Let's look at this one. The goal is to find the biggest number in a list. The logic is crystal clear, right? First, you just assume the very first number is the biggest one. Then you loop through all the others. If you find one that's bigger, that's your new champion. You just keep doing that until you reach the end, and voila, you're left with the biggest value. It's simple, logical, and ready to be turned into real code. All right, we've covered the what, the why, and the how. Now for the really fun part. Let's see how these simple ideas, these step-by-step instructions, scale up to power the incredible technology that we use every single day. First up, the absolute king of algorithms in our daily lives, Google search. We use it so much that it's easy to forget that it's basically magic. I mean, really, just stop and think about that. Billions and billions of pages, and it gives you an answer almost instantly. How is that even possible? Well, the answer is, of course, a whole bunch of incredibly clever and super efficient algorithms. So here's the secret. Google isn't searching the live internet every time you ask a question. It's searching its own massive pre-sorted index. Its algorithms match your keywords, use something called semantic analysis to figure out what you actually mean, and then, this is the crucial part, it ranks all those results using powerful algorithms like PageRank to decide what's most important. It's like a whole symphony of algorithms working together perfectly. Okay, now let's jump to another area where algorithms are creating pure magic: video games. Ever play a game and wonder how a character just seems to know exactly where they're going? I mean, they're not just following one single pre-programmed path. They have to react to you, to obstacles, to a world that's constantly changing. So how do they get from point A to point B without just running into walls or getting stuck? Well, they use these brilliant things called pathfinding algorithms, like the famous A-star search. At its core, A-star is an algorithm that's amazing at finding the most efficient path from one point to another. It uses what are called heuristics. You can think of them as smart rules of thumb or educated guesses to figure out which direction is the best bet. This is what creates that realistic, intelligent movement that makes modern games feel so alive. So, after all this, from baking cakes to writing code to building these incredible virtual worlds, what's the big takeaway? It's that an algorithm isn't just some nerdy computer thing. It's a fundamental tool for thinking. It's a way to break down any problem into logical, manageable, and totally solvable steps. And that leaves me with one final question for you. Think about your daily routine, a task you have at work, or even just a hobby. What everyday problem could you solve, or at least make a little easier by designing your very own algorithm for it? Thanks for joining me.